You ready to put everything we've talked about in this section all together? If you remember a few things back, I did outline the general steps to find the general solution. And then the last videos also talked about some qualitative analysis. So feel free to refresh, have your notes out. Also have your notes out because you hopefully should take notes here too. Okay, let's look at an example. So let's say that we're looking at the differential equation, the system of differential equations, dy dt is b times y, where b is the matrix 0, 2, negative 3, 2. And I'm giving you now an initial condition, y of 0 equals 1, 1. As a side note, this is a partially decoupled system. We could actually find solutions by first solving dx dt. Oh wait, no, it's not a partially decoupled system. Never mind. Dx dt only depends on y, but that's not helpful. If it was dx dt only depending on x, then it would be helpful. So just kidding. We can't solve it using methods of 2.4. So what I want you to do is I want you to start by pausing the video, finding your eigenvalues, and doing some qualitative analysis, saying what can you say with those eigenvalues. But don't worry, I'll also go through the steps, but I do want you to pause the video and find your lambdas and do qualitative analysis. What can you say? Can you make the whole phase portrait? We're gonna do it. Okay, pause it and go. So we remember that eigenvalues are the things that make this true. The matrix times the vector, the eigenvector equals the eigenvalue times the eigenvector. Our matrix is B here, so we'll write B. So in order for that to happen, we need BV minus lambda V equals 0. The way that we can do this is essentially B minus lambda times I, where I is the 2 by 2 identity matrix. This has non-trivial solutions. Remember, we had a theorem about that. It says non-trivial solutions when the determinant of that matrix equals 0. The determinant of this matrix is known as the characteristic polynomial. We're looking at the determinant of 0 minus lambda, negative 2, negative 3, 2 minus lambda. What is this determinant? It's negative lambda times 2 minus lambda plus negative 3 times 2. That's our characteristic polynomial. We want this to equal 0. So we're going to say negative 2 lambda plus lambda squared minus 6 needs to equal 0. That's a little weird. I'm going to multiply everything by a negative. That makes me happier. Oh, wait. No, I'm not. I'm going to just rearrange the terms. Lambda squared minus 2 lambda minus 6 equals 0. This is fun because I don't have notes for this. We're just solving it together. So I try to factor it. There's nothing that multiplies the negative 6, adds the negative 2. Not surprised. I'm expecting some complex eigenvalues here. You could complete the square. You could use a quadratic formula. Let's complete the square. It's a beautiful method. And we have a nice time for it too. So we're solving this equation. This is a perfect square if we add 1 to both sides. Wait a minute. I think I did something wrong. It's AD minus BC. I need to remember my determinants. Okay, great. So that's a minus, that's a plus, that's a plus, this is a minus. Okay, great. So this is lambda minus 1 squared equals negative 5. Okay, take the square root, add 1. Lambda is equal to 1 plus or minus 5i. Sorry, square root of 5 times I. We have found our eigenvalues. Remember, complex eigenvalues are always going to come in pairs like this. And so we know some things because of this, right? If lambda equals 1 plus or minus root 5 times I, we know the real part is 1. We know the imaginary part is square root of 5. Sorry if you don't like irrational numbers. I don't like irrational numbers. So what do we know? Is it a spiral source, spiral sink? Is it a center? It's complex, so it should be one of those. If we're looking at our phase portrait, which again we write in the xy plane, and actually we know our initial condition too, right? Our initial condition is x and y are both 1. So this is our initial condition, 1, 1. You might say, well, which way are we spiraling? We know it's a source because of the real part. We also know the period, right? We know the period is 2 pi over b. All right, the natural period is 2 pi over b, you might say. The natural frequency would be root 5 over 2 pi. That's how many cycles. This is how long it takes to do one cycle. The reciprocal is how many cycles happen per unit of time. But again, we need to find out which way we're spiraling. And after this section, you might be spiraling too. Okay, so multiple ways of doing that. One of them is just plugging in a point. You can plug in our initial condition, or you can plug in any other point. I like plugging in easy points. Let's plug in this point. What direction are we going at that point? This is what tells us what direction. All right. So we know that dy dt equals beta b, which is 0, 2, negative 3, 2. So if we look at the point 1, 0, for example, we multiply this out, we get 0, negative 3. You're going to notice a pattern, by the way. Choosing 1, 0 is really nice because it's always going to equal that. So our vector here is no x component and a downward y component. Okay, I guess we're going clockwise here. And that tells us that we have a spiral source. So we're spiraling out from here. So in previous time here, here's time equals 0, and then we're spiraling away. So I guess it's counterclockwise how we're going because it's the source. So we know what's happening. That's what our phase portrait looks like. That's all we need. And at any point we have, we can calculate this, and it's going to look something like that. Okay. And in fact, actually, it's going to have vertical, like our direction field's going to have vertical vectors at the x-axis. We could say a little bit more, but I think that's most of what I want to say for our qualitative analysis. Now I want you to pause the video and, oh gosh, where is it? Do steps 2, 3, and 4. Find me the general solution to this system of differential equations. So hopefully you did this, and if you got stuck or just want to check your work, feel free to watch this part. This was our complex eigenvalues. We only need one eigenvector, so let's only look at one eigenvalue. Maybe we don't care about the negative one. How do we find the eigenvector? The eigenvector is when b times the eigenvector is equal to lambda times the eigenvector. So we need to find out, okay, when is b, which is 0, 2, negative 3, 2, times some eigenvector equal to lambda, and again, you can choose whichever one you want, times that eigenvector. We'll have a system of equations. 0x plus 2y equals 1x, oh gosh, 1x plus root 5 I times x. And then the other one is negative 3x plus 2y needs to equal 1y plus root 5y times I. And again, these should always be redundant. It's not obvious that they're redundant. Many times it's not going to be obvious that they are redundant, but let's move everything over to one side and see whether they are or not. So we can subtract a 2y over, and then this becomes a 0 right here. And we can add all of this stuff over as well, make it 0. So plus 3x minus 2y equals 0. And again, it's still not obvious that it's redundant, right? And in fact, now I'm kind of wondering whether I should have rewritten it a little different way. Let's actually not set it equal to 0. Let's just solve this top one for x. I think that That might be a little nicer. Let's add 2y to both sides. This tells us the relationship between x and y. So for example, if x is 1, let's make x 2. If x is equal to 2, what is y? If x is 2, then we could factor out an x. And again, I'm sorry, this does get a bit tricky in terms of like, it's been a while since I've taught clear ways of doing this. All right, if x is 2, what does y have to be to make this true? Y has to be the other piece. 1 plus root 5 times I. And maybe this is the trickiest, weirdest part, depending on how your experience here. And over here, right, this can be simplified into negative y. Right, 1y minus 2y is negative 1. And then, oh, okay, we can rewrite this as 1y minus root 5 I times y equals 3x. If we add that over, and again, if x is, wait a minute, something weird happened. Because these should be redundant. This vector should satisfy both equations. And I think it does. I think it does. Right? If x is 2, we get 6. And if y is this, that's the conjugate. We get 1 minus 5i squared, which is 1 plus 5, which is 6. Okay, they are redundant. It's just hard to see. Whew. Again, I'm not doing this just for you. It is my recommendation, make sure that this eigenvector satisfies both equations. If they're not obvious that they're redundant, make sure that eigenvector you choose satisfies both. So we have our eigenvalue, we have our eigenvector, we have one complex valued solution. Specifically, right, lambda, we only need one of these, is 1 plus root 5i. Our eigenvector was 2 and then 1 plus root 5i. We can use this to find a single complex valued solution. And that is no different than it was for real valued. Eigenvector, eigenvalue. What is that? Well, that's where things get a little bit more interesting. 1 plus root 5i times t times our eigenvector. 2 and 1 plus root 5i, like so. Cool. We found a complex valued solution. Big whoop. Give me some real valued solutions, please. To do that, we're going to need good old Euler's formula. Remember, Euler's formula says e to the a plus bi is the same as, well, e to the a times e to the bi. And e to the bi was cosine of b plus I sine of b. So we're going to use Euler's formula to translate this into a different kind of complex valued solution. So we get e to the 1t, because a is 1, times cosine of root 5t. Be very careful. I don't care how you notate it, but be very careful that the t is not inside the square root. Sometimes people like end their square roots like this with a vertical slash. Plus I sine of root 5 times t. Sometimes I just give a little extra space here. But that's how we can use Euler's formula to transform that. And then again, we still have this over here. And now we need to split this up into a real part and an imaginary part. Whew. Okay, so let's get all the real stuff together. And again, we can keep an e to the t factored out of the real stuff if we wanted to. I think I want to. And then we can also have e to the t times I, or I times e to the t, depending on how you want to do it, or just e to the t times this and have I. Again, the order is fine. So what's the real part here? Well, the real part is going to be 2 times cosine of root 5t. And there's going to be, is that the only real part for the x coordinate? Yeah, because it's just 2 times this plus 2 times that. So this will be, again, 2 times the imaginary part, which is sine of root 5t. Oh gosh, let's not write it that far out. And I really should put parentheses, right? Because we should make sure that it's obvious that the t is inside of the cosine and the sine too. So much room for ambiguity here. Lovely. And then we have the imaginary part. Now be careful with the imaginary part. This is going to be a little annoying. I should probably have taken more steps of doing this. For the y component, right, the real part is cosine of root 5t. For sure, that's real. All right, but there's another real part as well. Again, there's an imaginary part that's sine of root 5t. I really should have done this in more steps. I'm committed now. But this is a complex number. We have to distribute. So they both get the real part, or they both get the 1, which we did that. And now they both get the root 5i as well. I mean, we're really foiling, to be honest. So when you multiply this by root 5i, we get a complex part. And that's going to be root 5 cosine of root 5t. And then we multiply this, we're going to get minus root 5 sine of root 5t. Okay. Whew. So let me check my answer, check my work, make sure that that we're good here. We got 2 cosine of root 5t, cosine of root 5t minus root 5 sine of root 5t. Good. And then the other one, the imaginary part, is 2 sine of root 5t, root 5 cosine of root 5t plus sine of root 5t. Great. I gave myself a little milepost. If we wanted to check, by the way, we don't need to check on notes that we took from the book. We could just check our answer by taking the derivative. This is supposed to be a complex valued solution to our differential equation. Should be able to take the derivative, use some product rules and some chain rules, and make sure it's true. Great. That's step 3, but we're almost done, sort of. Because there's actually there's a bonus step here. Oh gosh, how long is this problem? There's a bonus step because this is an initial value problem. So we're going to need a general solution and then go from there. Okay. Not to worry. This is the real part of the solution, and this is the imaginary part of the solution. Remember, the imaginary part of the solution does not have the I. Okay, so it does not include this I. If these are linearly independent at time t equals 0, and again, we can check that really easily. At time t equals 0, this is 1, 1. Sorry, this is 2, 1. And this is 0 root 5. Yep, they're linearly independent. So since they're linearly independent, they always will be. Still good to check. We have our general solution. We'll use that general solution to solve our initial value problem. So our general solution is, I'll give this a different name. Give this, I don't want to use y for both. It's going to be y of t equals any constant times one solution, and this was one solution, e to the t times 2 cosine of root 5t, cosine of root 5t, minus root 5 sine of root 5t. What a fun problem. All right, so a constant times one solution plus another constant times a linearly independent solution, which we have right here, this red guy. 2 sine of root 5t, and then sine of root 5t, plus root 5 cosine of root 5t. Isn't this awful? Oh gosh. I want to pause here. We're not done, but I want to pause because it really is awful, right? Doing this by hand. Remember way back when I was like, hey, we can take these steps and it might be a little tedious. It's a lot of calculus. It's a lot of algebra. Well, it's really just a lot of algebra. Or we can stop here and do qualitative analysis. This is why I said that. Because doing all of this, sometimes you don't need it. Sometimes we just need qualitative analysis. So it's very useful to be able to solve these by hand, but it is a lot. Does this look very nice? No, it doesn't. It's very cool that we can do that. It's very cool that we can use complex numbers to find real valued functions and solutions, but we don't always need this. We only need it sometimes. So again, reminding you of the power of qualitative analysis. But anyway, let's finish the problem. What was our initial condition? Our initial condition was that initially we were at 1, 1. So let's use that to find out what k has to be. So we're going to copy this to yet another page and plug in 1, 1. Sorry, we're going to say 1, 1 needs to equal what happens when we plug in t equals 0. T equals 0, that's 1. T equals 0, this is 2. T equals 0, this is 1. Oh, this is nice. T equals 0, that's 1. T equals 0, that's 0. T equals 0, that's root 5. As long as I didn't make any mistakes, which I'm sure I have, but don't worry. We can always check. So we get a systems of equations. 1 is equal to 2k1 plus 0, and 1 is equal to k1 plus root 5 k2. Okay, so k1 is a half. We use that to find out what k2 has to be. k1's a half, subtract it over. So k2 is 1 over 2 root 5. Oh, that actually is right. So we use that to get our general solution. And I actually can't erase because I copy and paste it. I really want to though. All right, let's write it down. We're done. We did it. Y of t is equal to k1, which was 1/2. E to the t times this nonsense. Cosine of root 5t minus root 5 sine of root 5t. All right, we're just plugging it back in. Plus k2, which is 1 over 2. And you could rationalize the denominator. I'm not going to, but you could if you wanted to. And then you just write down all of that. 2 sine of root 5t over sine of root 5t plus root 5 of cosine of root 5t. And you can't see it anymore because my head's blocking the way. But we have a solution to our initial value problem. And we're tired because this took 24 minutes to do one problem. We're tired. We just want to hit stop video, hypothetically, and move on with our lives by recording the next video. But we are going to be good math students. Okay? Let's look at this. Was our qualitative analysis right? I think we did check that already, right? Our qualitative analysis... Oh, no, we didn't. Well, let's check our qualitative analysis. What is our... Does this match what we thought it should match? So our differential equation was... This was 2 times y, and dy dt was negative 3 times x plus 2 times y. And yes, I know it's been a long video. Feel free to pause or just stop at this point. We're going to check our answer and do some I want to model some good behavior. Okay. So we see that it is indeed a spiral source. Okay. And is it moving the same direction we said it should move? Oh, crap. Wait, no, it's not. Oh, ha. Okay, so we did make a mistake. Right, we didn't follow our arrow. It's because I forgot it was a source and I tried to fix it by changing other things. So yeah, sorry about that. This is why we check our answers. All right, it is a spiral source, which means we need to be moving away. So it's moving towards in that other direction. Okay, good. That makes sense. So again, we need to be following those arrows. We should have that down vector at any time. So that means we're going clockwise, like I originally said before I fixed it in the wrong way. We're spiraling out. Okay, cool. And again, we could see that if we start at 1, 1, as we're starting, my cat just knocked something down. She climbed to the very top tower, found the cat treats, and then knocked the cat treats down, and they exploded all over the carpet. Whole box of cat trees so she could eat them. So she lost her roaming privileges. She's stuck in here to learn differential equations now. But this lets us continue to check our answer, because if we graph the x and y here, for, again, the x will be the blue, the y will be the orange, and again, this is our t-axis on the horizontal axis. The vertical axis will either be x or y accordingly. Then what you can see is exactly what we wanted to see, right? The initial condition is 1, 1. What are we seeing? Well, initially, let's look at x first, the blue. Initially, x is growing a bit, but only a tiny bit. And then it'll get small, even more negative, and then it'll get even more positive, and so on. Is that what x is doing with this initial condition? Yeah, normally it's growing a bit, and then it's getting smaller, and then it's getting, all right, it's gone off, right? But we can see that that behavior is getting modeled. Y is also starting off at 1, just like it was supposed to. Y is initially shrinking. It gets negative, and then it gets very positive. Y is initially shrinking, good. And then around, it'll go off, but it'll start getting very positive after that. So we can see exactly the kind of behavior that we expected from our qualitative analysis, making us feel pretty good that our analytic solution's pretty correct as well. Okay, so that's pretty much it for this video. Again, doing general solutions for these problems can take a long time. Practice is going to help make it go faster. And then again, remember to do qualitative analysis along the way to kind of check your work. Hope you enjoyed this fun little practice video. We have more practice in the next one. I won't do the whole thing, so it won't be 30 minutes again, but I will give you answers, little goalposts for you to check along the way if you want more practice. Bye-bye.